The deepest corners of space hide monsters from the dawn of time. We are talking about the universe's most distant black holes, cosmic giants that formed when everything was new. By the end of this journey, you will understand how these ancient behemoths are rewriting the story of our entire cosmos. We will uncover how they grew so big so fast and why their very existence might be impossible. What single discovery about our universe still fills you with wonder? Distance is a trick of the light in our universe. When we call a black hole the most distant, we are not just pointing to a faraway dot on a map. We are launching a time machine. The light from these ancient objects has been traveling through the expanding cosmos for over 13 billion years to reach our telescopes. That means we are not seeing them as they are today. We are seeing them as they were when the universe itself was less than 1 billion years old, a mere infant compared to its current age. This is what astronomers call look-back time. Every photon is a messenger from the past carrying a snapshot of cosmic infancy. To measure this incredible journey, scientists rely on a phenomenon called redshift, symbolized by a simple letter Z. As the universe expands, it stretches the wavelength of light traveling through it, shifting it toward the red end of the spectrum. The higher the Z value, the greater the stretch, the farther the light has traveled, and the further back in time we are looking. A black hole with a redshift of 7, for example, shows us a universe only about 700 million years after the Big Bang. So when we talk about the most distant black holes, we are really discussing the oldest portraits we possess, grainy, faded pictures of the universe's first monstrous children. That ancient light has a name and a face. Meet the current champion of cosmic distance, a quasar known as J0313-1806. Its technical designation hides a breathtaking reality. This object holds the record for the most distant quasar, and therefore its central supermassive black hole ever observed. The number that defines it is a redshift value of 7.64. That single, staggering figure tells us we are witnessing this object as it existed a mere 670 million years after the Big Bang. To put that in perspective, the universe was only about 5% of its current age. Yet, at its heart lies a gravitational monster of incomprehensible scale. The black hole powering this quasar is estimated to weigh over 1.6 billion times the mass of our own Sun. This is not just a big black hole, it is a cosmic paradox. How does something grow to be over 1 billion solar masses in less than 1 billion years? This is the heart of the seed problem, a fundamental mystery that challenges our understanding of how the first structures in the universe formed. It should not have had enough time to feast on so much material. Beyond its impossible mass, this quasar is a violent beacon. It is actively ejecting a jet of superheated material at nearly 1/5 the speed of light, a brilliant lighthouse shining across the eons. To capture this faint whisper from the dawn of time required a technological marvel on our own world, the Atacama Large Millimeter Array in Chile. This network of radio telescopes, sitting high in one of Earth's driest deserts, acted as a single, colossal ear, listening for the faint radio hum of this ancient cataclysm. It found not just a black hole, but a question written in light demanding an answer. This brilliant beacon of ancient violence reveals a deeper truth about our search. We do not actually see the black hole itself. We see the desperate, screaming light of its last meal. These most distant objects are not simply black holes in the dark. They are quasars, the hyperactive hearts of the universe's first galaxies, and they are visible only because of a catastrophic act of consumption. Picture the scene at the core of that infant galaxy 13 billion years ago. An embryonic supermassive black hole, a gravitational pit of pure darkness, sits at the center. Around it, a vast whirlpool of gas, dust, and even entire stars, stolen from the surrounding galaxy, spirals inward. This is the accretion disk, a cosmic maelstrom where friction heats the material to millions of degrees. It glows with a ferocious, blistering light across the entire electromagnetic spectrum, from radio waves to X-rays. This is not the black hole shining. It is the black hole's dinner plate glowing white-hot as the food is torn apart just before it vanishes forever. The energy released in this process is almost beyond comprehension. A single, feeding supermassive black hole can outshine every single star in its host galaxy combined, making the quasar the brightest persistent object in the entire universe. This is our window. Without this frenzied feast, without the quasar phase, these ancient black holes would be utterly invisible to our telescopes, hidden in the black velvet of the early cosmos. Their incredible hunger is the very reason we know they exist at all. We are cosmic detectives, finding the monster by the brilliant glow of the fire it lights. That brilliant, violent light from the first quasars did more than just announce their presence. It changed the very fabric of the cosmos. To understand how, we must go back to a time before any stars or black holes, to a universe that was not clear but foggy. After the Big Bang, the cosmos was a hot, dense soup of particles that slowly cooled. For hundreds of thousands of years, it was filled with a thick fog of neutral hydrogen gas opaque to light. This era is called the Cosmic Dark Ages. The universe was a shadowy realm. Then, the first stars and galaxies ignited. Their intense ultraviolet radiation began to strip electrons from those neutral hydrogen atoms, a process called reionization. Think of it as a cosmic sunrise, burning away the morning mist to make the universe transparent. For decades, astronomers believed the powerful ultraviolet beams from early quasars, like the record holder we just discussed, were the primary flashlights that cleared this fog. They seemed like perfect culprits, blazing with enough energy to ionize vast regions of space. But here lies the cosmic dawn challenge. As our telescopes peer deeper, we are finding a puzzling crime scene. Those brilliant, supermassive black hole quasars from the universe's first billion years are incredibly rare. They are the dazzling exceptions, not the rule. There simply are not enough of them to have reionized the entire cosmos by themselves. The math does not add up. So if not these monstrous behemoths, then who or what provided the immense amount of energy needed to transform the entire universe from opaque to clear? The current leading suspect is a crowd of faint, early galaxies, trillions of them, each too dim to see individually from our vantage point but collectively powerful. Their combined, gentle glow from countless newborn stars might have been the true engine of reionization, a diffuse cosmic dawn rather than a few blinding spotlights. This reshapes our entire model of the universe's first chapters. It suggests that the hard work of building a transparent cosmos was not done by a few spectacular giants, but by an unimaginable multitude of tiny, faint lights working together in the dark. The search is now on to find and count these elusive infant galaxies, to solve the mystery of how our universe woke up and became the brilliant, see-through expanse we observe today. The mystery of the cosmic dawn is matched only by the puzzle of the seeds themselves. If those early supermassive black holes grew to billions of solar masses impossibly fast, what did they grow from? What kind of seed could possibly sprout into a billion solar mass monster in less than a billion years? Astronomers have three main theories, and each one pushes the limits of physics. The first and most straightforward idea is that they grew from the collapsed cores of the universe's very first stars. These are called population 3 stars, and they were nothing like the stars we see today. Born from pure hydrogen and helium with no heavier elements, they could have been colossal, perhaps hundreds of times the mass of our Sun. When such a behemoth died, it would have collapsed directly into a black hole of maybe a few hundred solar masses. That is a formidable starting point, but there is a problem, a big one. Even a black hole seed that massive would have to consume matter at the maximum possible rate for its entire life, without pause, to reach a billion solar masses by the time we see it. It is like expecting a sapling to become a giant redwood in a single season. It requires perfect, gluttonous conditions that may simply not have existed. The second theory proposes a shortcut, a cosmic cheat code. Perhaps these seeds never went through a star phase at all. In the dense, turbulent clouds of the early universe, massive clumps of primordial gas could have collapsed directly under their own gravity, bypassing star formation entirely and forming a black hole seed of perhaps 10,000 solar masses or more right from the start. This direct collapse black hole scenario provides a much bigger seed, giving it a head start in the race to become supermassive. But it requires very specific, pristine conditions, a cloud that can cool enough to collapse but not so much that it fragments into many smaller stars instead. It is a delicate and rare cosmic recipe. The third theory looks to the power of crowds. In the dense core of a young galaxy, a massive cluster of early stars could have formed. Through dynamical friction, a sort of gravitational traffic jam, these stars could have collided and merged, their cores sinking to the center to form a single, massive object that then collapses. This could also create a sizable seed. Yet again, the timeline is punishing. Each of these theories can produce a seed, but the leap from that seed, whether it is 100 or 10,000 solar masses to a billion solar mass titan in mere cosmic moments, remains the central, unresolved tension. The seeds exist in our models, but their growth spurt defies easy explanation, pointing to a frantic, violent infancy for the cosmos that we are only beginning to piece together. The punishing timeline for these ancient giants introduces a fundamental law of physics they seem to have broken. Every black hole, as it feeds, faces a speed limit. This is the Eddington limit, a cosmic rule born from a simple balance of forces. As matter falls into a black hole, it releases immense radiation which pushes outward. The Eddington limit is the point where this outward radiation pressure perfectly balances the inward pull of gravity. Feed any faster, and the radiation blast would blow away the very gas and dust the black hole is trying to consume, shutting off its own meal. It is the universe's way of saying you can only eat so quickly. For a black hole to grow, it must dine at or below this speed limit. Now consider our billion solar mass black hole from the universe's infancy. To reach that staggering weight in under a billion years, even starting from a hefty seed, it would have needed to feed at the maximum Eddington rate for nearly its entire existence. That is not just a steady diet, it is a perfect, uninterrupted, gluttonous feast lasting hundreds of millions of years. It is the astrophysical equivalent of winning the cosmic lottery every single day without fail for longer than dinosaurs walked the Earth. The odds of such a perfect, stable environment persisting for so long in the chaotic early universe seem vanishingly small. This is the growth speed limit these objects defiantly ignore, forcing scientists to consider a more chaotic and violent possibility. Perhaps these black holes did not dine politely. Maybe they binge ate. The theory of super-Eddington accretion suggests that in the dense, gas-rich nurseries of the first galaxies, a black hole could occasionally gorge itself at rates far above the standard limit. In these short, violent bursts, the inward pull of gravity could temporarily overwhelm the outward radiation pressure, allowing vast amounts of material to crash through in a chaotic downpour. Think of it not as a steady sip from a straw, but as someone occasionally upturning the entire bowl. These frenzied episodes could allow for explosive growth spurts, helping a black hole put on weight much faster than the standard rules would allow. The key question now is whether the early universe provided enough of these dense gas reservoirs to fuel repeated binges, and whether the black holes could survive them without blowing their food supply away entirely. This frontier of research is where our understanding of physics meets the brute force evidence of the cosmos, searching for the loophole that let the universe's first monsters grow up too fast. That frantic feeding frenzy does more than just make the black hole grow. It transforms the very chemistry of the cosmos. The material swirling in those ancient accretion disks and being blasted out in jets is not just fuel, it is a cosmic forge of unimaginable power. Within the maelstrom, where temperatures soar to millions of degrees and pressures crush atoms, something miraculous happens. The simple, primordial elements left over from the Big Bang, hydrogen and helium, are fused together into heavier, more complex atoms. Carbon, oxygen, nitrogen, and even iron are forged in the heart of this violence. These are the very elements that form the bedrock of planets, oceans, and life itself. But a forge is useless if its products are locked away. These early black holes, through their explosive deaths or their powerful, galaxy-spanning winds, act as cosmic distributors. They violently seed their host galaxies and the vast reaches of intergalactic space with these newly minted metals, a process astronomers call chemical enrichment. This means that long before most galaxies had even properly formed, these distant quasars were already polluting the pristine cosmos with the raw ingredients for future complexity. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were first forged in the hearts of stars or in cataclysms like these, then scattered across the universe by these ancient, erupting giants. They were the universe's first factories and delivery trucks, working at a breakneck pace to enrich a cosmos that was still in its infancy, setting the stage for everything that would follow. But this brilliant, violent factory cannot run forever. The very quasars that allow us to see these distant black holes represent just a fleeting, screaming phase in their impossibly long lives. The notion of a perpetually active, glowing monster is a cosmic illusion. Every quasar is fueled by a finite supply of gas, a cosmic reservoir that will eventually run dry. When the feast ends, the light goes out. The furious accretion disk dwindles, the blinding glare of superheated material fades, and the black hole slips into a state of dormancy. It becomes a silent, sleeping giant, its immense gravity still present but no longer announcing itself with a beacon visible across the universe. This life cycle means the distant quasars we have managed to detect are the rare exceptions, the brief moments of cosmic violence caught in the act. For every single brilliant, active quasar we see shining from the early universe, astronomers suspect there could be thousands, perhaps even millions, of identical black holes that are simply quiet. They are the dark majority, hidden in the shadows of their infant galaxies, invisible to our current telescopes. This presents a profound challenge. How do you take a census of a population when you can only see the members who are screaming? Estimating the true total number of supermassive black holes that existed in the cosmos's first billion years becomes an exercise in cosmic guesswork. It is like trying to count all the bears in a vast, dark forest by only spotting the ones that are currently roaring. The silent ones could be everywhere, and their hidden presence means the early universe might have been far more crowded with these gravitational monsters than its brilliant but sparse beacons would have us believe. Our inability to see the silent majority of these ancient giants presents a fundamental problem, but nature itself provides a solution. Einstein's theory of general relativity gives us a helping hand in the most literal sense. His revolutionary idea stated that mass warps the very fabric of space and time, and light must follow these curves. This prediction leads to a phenomenon called gravitational lensing. Imagine the gravity of a massive object like a giant cluster of galaxies, acting not as a wall but as a lens in space. When light from a far more distant object, like an early quasar, travels toward us and passes by this massive foreground cluster, its path is bent. This warping can distort, multiply, and most importantly for our search, dramatically magnify the light of the background object. It is a natural cosmic telescope built into the architecture of the universe itself. This effect has been absolutely crucial in our hunt for the faintest whispers from the dawn of time. Some of the most distant quasars we have detected are so incredibly faint that their light would be a mere smudge, utterly lost in the glare of their own foreground galaxies without this cosmic magnification. In one extraordinary case, astronomers discovered a quasar from the universe's first billion years whose light was magnified by a staggering factor of 50. That is the difference between trying to read a book from a mile away and having that same book placed directly in your hands. This gravitational boost does more than just make a dim object visible. It allows us to study it in unprecedented detail. We can begin to analyze the structure of its accretion disk, measure the winds blowing from its core, and probe the chemistry of its host galaxy in ways that would be utterly impossible without this free cosmic gift. Gravitational lensing turns the universe's own gravity into our most powerful observatory, revealing the hidden children of the cosmic dawn. Gravitational lenses not only reveal hidden black holes, they unveil the chemistry of their ancient homes. In the swirling chaos of a quasar's accretion disk, a staggering discovery was made. Astronomers detected the unmistakable signature of water vapor swirling in the maelstrom around a supermassive black hole observed just 1.6 billion years after the Big Bang. This is not a puddle or an ocean. This is water as a hot, diffuse gas, trillions of times more massive than all the water on Earth, existing in a place of unimaginable violence. Alongside it, other complex molecules like carbon monoxide were found. This changes everything we thought about the timeline of cosmic chemistry. The universe was not a simple, empty place for long. In the furious environments around these first monsters, the fundamental ingredients for complexity were being assembled at a breakneck pace. Water, that essential molecule for life as we know it, was already present when the cosmos was a mere toddler. This forces a profound shift in perspective. The chaotic nurseries around infant supermassive black holes were not just engines of destruction. They were also cosmic kitchens, churning out and dispersing the very molecules that would one day become the building blocks of planets and perhaps biology. It suggests the conditions for interesting chemistry and potentially the raw materials for life were established far, far earlier than anyone dared to predict, all within the shadow of the universe's most violent object. That cosmic kitchen is invisible to the human eye. The brilliant ultraviolet blaze from those ancient quasars never reaches our planet in a form we can see. The relentless expansion of the universe performs a cruel magic trick on their light. As the light from a 13 billion-year-old quasar travels across the ever-stretching cosmos, its wavelengths are stretched along with space itself. What began as searing ultraviolet radiation, the kind that gives you a sunburn, gets pulled, lengthened, and transformed. By the time this ancient signal completes its epic journey to Earth, it has been redshifted out of the visible spectrum entirely. It arrives not as visible light, but as infrared radiation, a form of light we perceive as heat. For the most distant objects, this stretching is so extreme that their light is pushed even further into the faint whispers of the radio spectrum. This creates a fundamental observational challenge. Our eyes and the optical telescopes built to mimic them are utterly blind to these most distant beacons. They are shining in a color the human race cannot perceive. To see them, we had to invent new eyes. This is why missions like the James Webb Space Telescope are not just improvements, they are revolutions. Perched a million miles from Earth, its gold-coated mirrors and sophisticated instruments are specifically designed to be exquisitely sensitive to infrared light. It is not looking for the universe as it is now, but for the universe as it was by catching the stretched, faded glow of its infancy. On the ground, observatories like the Atacama Large Millimeter Array act as colossal ears, tuned to the faint radio hum of these ancient cataclysms. Every discovery of a record-breaking distant quasar is a testament to this technological leap, a triumph of engineering that allows us to translate the invisible heat signatures of the cosmic dawn into images and data we can finally understand. We are not just looking farther, we are learning to see in a whole new light. This incredible power defines their role in the cosmic ecosystem. A single, feeding supermassive black hole can produce a luminosity thousands of times greater than all the hundreds of billions of stars in its host galaxy combined. Let that scale sink in. Picture a single, brilliant lighthouse, no bigger than a house, that shines so fiercely it outshines every streetlight, every window, every neon sign in the entire sprawling metropolis built around it. That is the relationship between a quasar and its galaxy. All the collective starlight from hundreds of billions of suns is utterly drowned out by the furious glow from a region of space not much larger than our own solar system. This is not a gentle light. It is a torrent of radiation across the entire spectrum, from radio waves to lethal X-rays, pouring out from the material just moments before it vanishes forever into the black hole's event horizon. That energy output is so immense it becomes a dominant force, shaping the destiny of everything around it. This dazzling light does more than just announce a monster's presence. It can actually stifle the very creation of new stars in its host galaxy. The same radiation that makes the quasar visible to us across billions of light years acts like a cosmic hurricane, blasting through the galaxy's vast reservoirs of cold gas and dust. These clouds are the nurseries where stars are born, and the quasar's intense radiation heats them up and blows them apart, preventing them from collapsing under their own gravity to form new suns. In this way, the most distant black holes were not just passive inhabitants or even chaotic builders. From the universe's infancy, they acted as powerful regulators of galactic evolution. They could, in essence, put a cap on the growth of their own homes, turning off the star formation factory with the sheer brilliance of their own catastrophic feast. This creates a fascinating feedback loop where a galaxy feeds its central black hole, and the black hole, in turn, dictates how that galaxy is allowed to grow, a relationship of creation and control that was established in the first chapters of cosmic history. The search for these ancient monsters has entered a new golden age thanks to a single, revolutionary eye in the sky. The James Webb Space Telescope is not just another observatory, it is a time machine specifically designed for the cosmic dawn. Before its launch, the number of confirmed quasars from the universe's first billion years, those beyond a redshift of 7, could be counted on 2 hands. They were the rare, dazzling exceptions stumbled upon through luck and immense effort. Now, James Webb is changing the game entirely. Its unparalleled sensitivity to infrared light, the stretched and faded glow of the early universe, allows it to conduct systematic surveys of the ancient sky. Instead of finding 1 or 2 record breakers, it is finding them in significant numbers, including tantalizing candidates that could shatter the current distance record. James Webb is turning a trickle of discoveries into a steady stream, revealing that these objects, while still rare, were a fundamental feature of the infant cosmos. One of its earliest and most profound discoveries was not about the black hole itself, but about its home. For decades, the blinding glare of a quasar made it impossible to see the faint, nascent galaxy that hosted it. It was like trying to see a candle flickering right next to a blazing spotlight. James Webb's precision finally pierced that glare. In one landmark observation, it directly confirmed the presence of the host galaxy around a quasar from when the universe was just 700 million years old. For the first time, astronomers could study not just the brilliant central monster, but the struggling galaxy trying to form around it. The picture that emerged was startling. This young galaxy was a chaotic, compact place, already brimming with stars and dust, but it was also being violently reshaped by its own brilliant heart. James Webb's data showed powerful winds driven by the quasar's radiation, blasting outwards at speeds of over 1 million miles per hour. These winds were simultaneously enriching intergalactic space with heavy elements and potentially blowing away the galaxy's future fuel for star formation. This complete view transforms a distant point of light into a dynamic, living system. We are no longer just finding beacons, we are pulling back the curtain on entire cosmic ecosystems in their infancy, watching the dramatic and intimate dance between a growing galaxy and the ravenous giant at its core. The violent winds from those infant quasars reveal a deeper architectural secret. One of the biggest surprises from our new cosmic census is where these ancient monsters chose to live. Logic would suggest that a billion solar mass engine of destruction requires a grand, majestic home, a colossal and well-ordered galaxy worthy of its power. The reality, as seen through the piercing infrared eyes of James Webb, is far more chaotic. Many of these most distant quasars are not seated at the heart of mighty, structured spiral or elliptical galaxies. Instead, they are found in what can only be described as cosmic construction sites, messy, clumpy, and surprisingly compact environments. These are not finished galactic mansions, they are the raw frameworks, the beams and girders of a galaxy still being assembled. This observation is revolutionary. It suggests a timeline we got backwards. For years, the prevailing model was one of co-evolution, a polite partnership where a galaxy forms first, and its central black hole grows slowly over time within the safety of that established structure. But these messy environments tell a different, more dramatic story. They indicate that the supermassive black hole formed first, or at least grew to immense size incredibly early, while its host galaxy was still a ragged, turbulent cloud of gas and stars. The black hole was not a quiet tenant moving into a finished home. It was the foundational seed, the gravitational anchor, around which the entire galaxy coalesced. Its immense gravity would have acted as a focal point, pulling in vast streams of primordial gas from the cosmic web. This infalling material fed the black hole's furious growth, while the shocks and turbulence from the process itself could have triggered the rapid formation of the galaxy's first stars. In this inverted model, the brilliant quasar phase is not a late-stage feature of a mature galaxy. It is the violent birth cry of the galaxy itself. The monster does not inhabit the core, it builds the core. This turns our understanding of cosmic structure inside out, painting a picture where the darkest objects in the universe were the architects of the first light. This ancient light is a cosmic tape recorder. As the brilliant beam from a distant quasar travels for billions of years toward us, it does not move through empty space. It passes through the diffuse fog of neutral hydrogen gas that filled the early universe, and that fog leaves a mark. When the quasar's light, particularly at a specific ultraviolet wavelength called Lyman alpha, encounters a cloud of this hydrogen, the gas absorbs that precise slice of light. Each cloud the beam passes through steals another little piece. By the time the light finally reaches our telescopes, its spectrum, the detailed breakdown of its colors, is not a smooth rainbow. It is riddled with a series of dark absorption lines, a barcode of shadows. Astronomers call this the Lyman alpha forest, and it is one of the most powerful tools in all of cosmology. Each dark line is an imprint, a fossil record of a specific cloud of primordial hydrogen that existed at a specific distance, and therefore a specific time between us and the quasar. By mapping the spacing and depth of these thousands of lines, scientists can reconstruct a one-dimensional map of the distribution of matter in the ancient cosmos. It is like listening to the echo of a single shout in a vast, foggy canyon. The pattern of the returning echoes tells you the shape of the canyon walls. This forest allows cosmologists to chart the cosmic web in its infancy, tracing the filaments and voids where the first galaxies would eventually form. But the revelations go even deeper. The precise spacing of these lines depends on fundamental constants of nature, like the fine structure constant, which governs the strength of electromagnetism. By comparing the forest in the light of incredibly distant quasars to the same patterns in laboratories on Earth, we can ask a staggering question. Have the laws of physics themselves remained unchanged over 13 billion years? Is the universe's rulebook the same today as it was at its birth? So far, the answer seems to be a tentative yes. The constants appear constant. But each new, more distant quasar provides a more stringent test, a chance to listen for a whisper of change in the universe's most basic rules, all encoded in the shadowy fingerprints left on light from the dawn of time. The shadowy fingerprints on ancient light point to a cosmos already structured, but perhaps that structure was born from something even older and more exotic. Our entire journey has assumed these distant giants grew from something, whether a collapsed star or a gas cloud. But what if they did not grow at all in the traditional sense? What if they were simply born huge, as ready-made monsters from the universe's very first moment? This radical idea leads us to primordial black holes. These are not the black holes of stellar collapse or galactic cores. They are hypothetical relics thought to have formed not from dying stars, but from the intense, chaotic pressures in the first tiny fraction of a second after the Big Bang. Imagine the newborn universe as a seething, dense broth. Within that broth, random quantum fluctuations could have created pockets of matter so incredibly dense that they collapsed directly into black holes. This would have happened long before the first stars flickered on, long before the first atoms even formed. The scale of these objects could be almost anything. A primordial black hole could be as small as an asteroid, with the mass of a mountain squeezed into a space smaller than an atom. Or it could be as massive as thousands of suns, a titanic seed delivered to the cosmos fully formed. This wild idea solves two profound mysteries at once. First, the dark matter puzzle. We know most of the matter in the universe is invisible, exerting gravity but not emitting light. Could that dark matter be, at least in part, a vast swarm of asteroid-mass primordial black holes drifting between the stars? They would be nearly impossible to detect individually, yet their collective gravity would perfectly explain the motions of galaxies. Second, and more directly to our story, the seed problem. If some of those primordial black holes were born with masses of 10,000 or even 100,000 suns, they would be perfect ready-made seeds for the quasars we see in the early universe. They would not need to race against time, growing from a stellar remnant. They would arrive on the scene in the infant cosmos already supermassive. The galaxy could then assemble around this pre-existing gravitational anchor, explaining how we see billion solar mass monsters so soon after the Big Bang. It is an elegant, if speculative, solution. The catch is, we have never definitively found one. Their existence remains a compelling what-if, a ghost in the equations of cosmic dawn, reminding us that the universe's first chapters might have been stranger than we dare to imagine. These ancient monsters had weapons that could reshape entire neighborhoods of the cosmos. Beyond the blinding light of their accretion disks, some of these early supermassive black holes unleashed something even more destructive: relativistic jets. Picture a beam of energy so focused and powerful it punches out from the black hole's poles at nearly the speed of light. This is not a gentle spray of light. It is a cosmic firehose composed of superheated plasma and magnetic fields, a particle accelerator on a galactic scale. In the crowded, gas-rich environment of the early universe, these jets had room to run. They could propagate for hundreds of thousands of light years, a distance far exceeding the size of their own infant host galaxies. A single jet could stretch from one side of our entire Milky Way to the other and keep on going, a searing scar across the embryonic cosmos. The energy these jets inject into the surrounding void is almost incomprehensible. They slam into the thin gas of the intergalactic medium, the cosmic web of hydrogen that fills the space between galaxies, and violently heat it. This creates a profound feedback effect on a truly colossal scale. By superheating this primordial gas, the jets prevent it from cooling down, collapsing, and eventually condensing to form new stars in neighboring proto-galaxies. Think of a young sapling trying to grow in a forest that is constantly being swept by a blowtorch. The jet essentially sterilizes vast regions of space, dictating which pockets of the universe are allowed to build stars and which are condemned to remain barren, hot, and diffuse. This means that from the universe's earliest epochs, the most distant black holes were not just inhabitants of their own galaxies. They were cosmic overlords, using their relativistic jets to sculpt the large-scale structure of the cosmos itself, influencing the fate of galaxy clusters that had not even begun to form. Their reach extended far beyond their own event horizons, writing the rules of construction for everything that would come after. The evidence from these messy construction sites points to a startling conclusion. The oldest, most distant quasars are not guests in finished galactic homes. They are the foundations upon which those homes were built. This turns the classic cosmic chicken or egg problem on its head. For decades, astronomers assumed a mature galaxy came first, providing a stable nursery where a central black hole could slowly grow over eons. But the violent, compact environments we now see suggest the opposite sequence was often true in the early universe. A massive black hole seed formed incredibly early, acting as a gravitational anchor in a swirling chaos of primordial gas. Its immense pull drew in vast streams of material from the cosmic web, feeding its own furious growth while simultaneously creating the dense, turbulent conditions perfect for sparking the birth of the galaxy's first stars. The monster did not move into the house, it laid the cornerstone and summoned the builders. This dual role as both creator and destroyer is the key to understanding their architectural power. The same ferocious energy that defines a quasar has two opposing galaxy-shaping effects. On one hand, the intense radiation and powerful million-mile-per-hour winds can have a sterilizing effect. They blast through clouds of cold gas, the raw material for new stars, heating them up and blowing them apart before they can collapse. This quenches star formation across vast regions, effectively putting a cap on the galaxy's growth. Yet, in a beautiful paradox, this violence can also be generative. When those supersonic winds slam into denser pockets of gas farther out in the galactic halo, they don't just scatter them, they compress them. Imagine a powerful shockwave moving through a cloud. It crushes the material in front of it into incredibly dense, cool knots. These knots, now far denser than before, can suddenly meet the critical threshold for gravitational collapse. In this way, the black hole's fury can trigger explosive bursts of new star formation in a ring or shell around the galactic core. It is a cosmic feedback loop of breathtaking complexity. The central black hole feeds, unleashes hell, which simultaneously shuts down star birth in its immediate vicinity, while sparking a firestorm of new suns on the galactic frontier. This makes the most distant black holes the ultimate architects of their domains from the very beginning. They were not passive inhabitants, they were active foremen on the construction site of the early cosmos, using gravity as their blueprint and radiation as their tool. Their growth and activity dictated the pace, pattern, and very structure of the galaxies growing around them. A more massive, active black hole could create a more massive galactic bulge of stars at its center. Its jets could carve out channels and heat the surrounding intergalactic gas, determining how much fuel remained for future growth. This intimate, dynamic partnership, forged in the universe's first billion years, set a template that appears to have continued throughout cosmic history. The supermassive black hole at the heart of our own Milky Way, now quiet and dormant, likely played a similar shaping role in its distant youth. Every giant galaxy we see today may therefore carry the lasting imprint of the ancient, ravenous giant that once roared at its core, a silent architect whose violent birth cries determined the shape of its home for all time. This architectural power stems from physics pushed to its breaking point. These most distant black holes are more than ancient monsters. They are the universe's ultimate natural laboratories. To understand them, we must test our theories in arenas of unimaginable violence, where gravity is so strong it twists the fabric of space-time itself into a closed loop. The environment around a supermassive black hole is a place where matter does not behave in any familiar way. The accretion disk is a cauldron of plasma physics, a superheated soup of charged particles where magnetic fields become tangled ropes of energy, capable of flinging material inward or launching it outward in those colossal jets. This interplay of magnetism and fluid dynamics, called magnetohydrodynamics, is a fiendishly complex dance we can only approximate in supercomputers. Observing the real thing in these distant quasars gives us a masterclass in how the universe actually operates under forces we can never hope to recreate on Earth. But the experiments run even deeper. Every photon that reaches us from a quasar 13 billion light-years away has performed a specific test for us. It has traveled across an expanding universe, its path potentially bent by the warped spacetime of intervening galaxies and clusters. By comparing its journey to the predictions of Einstein's general relativity, we are conducting a continuous billion-year audit of the theory's accuracy. Has gravity behaved exactly the same across all of cosmic history? So far, the light from these distant beacons says yes. Furthermore, that ancient light carries within it the spectral fingerprints of atoms, the precise energy signatures of elements forged in the early universe. By comparing those fingerprints to the ones we measure in laboratories today, we can ask a profound question. Have the fundamental constants of nature, the very numbers that govern the strength of forces like electromagnetism, remained truly constant? Could the fine structure constant, which dictates how atoms hold together, have been slightly different 13 billion years ago? A single, tentative detection of such a drift would revolutionize physics. These black holes, by acting as brilliant backlights shining through the infant cosmos, give us our only chance to run this experiment. They are not just objects we study, they are the most precise instruments we have for probing the stability of reality itself, time capsules that hold the answer to whether the universe's rulebook has always been the same. The stability of reality is one test, but the census of these ancient giants is another, and our current view remains frustratingly incomplete. We have been studying the dazzling exceptions, the rare monsters caught in a screaming phase, while the silent majority hides in the dark. The next leap in understanding will not come from staring harder at the few we know, but from finding thousands more, and for that we need a new kind of eye on the sky. Enter the next generation of cosmic explorers, telescopes designed not just to see farther, but to see wider and deeper than ever before. The Nancy Grace Roman Space Telescope, set to launch later this decade, will revolutionize our search with a single superpower, an enormous field of view. While the James Webb Space Telescope is a powerful magnifying glass, perfect for studying a single ancient quasar in exquisite detail, Roman will be like a wide-angle lens on the universe. It will conduct vast, deep sky surveys, mapping enormous swaths of the cosmos in infrared light. Its mission is to find not just one or two record breakers, but to discover thousands of distant quasars from the first billion years. This statistical power changes everything. Instead of puzzling over individual oddities, we will finally be able to build a true demographic picture. How common were these objects really? What were their typical masses? How did their numbers evolve as the universe aged? Roman will give us the data to answer these questions, transforming black hole science from the study of spectacular singularities into a rigorous field of population statistics. We will see the full forest, not just the tallest, most bizarre trees. But what about the seeds themselves, the mysterious objects that existed before the quasars ignited? To find those, we must listen rather than look and tune our instruments to a different kind of signal. This is the promise of the Square Kilometre Array, or SKA. This is not a single dish, but a vast network of radio antennas spread across South Africa and Australia, designed to function as one colossal radio telescope with a total collecting area of, you guessed it, about 1 square kilometre. Its sensitivity to faint radio waves will be unprecedented. The SKA aims to detect the faint thermal whisper, the gentle radio glow, from the accretion disks of supermassive black holes in the very earliest galaxies, perhaps even before they entered their brilliant quasar phase. Think of it as hearing the deep, quiet rumble of a stomach before the feast begins, before the table is set ablaze. Detecting these faint, nascent black holes would be the ultimate prize. It would allow us to finally witness the seed population directly, to see how many there were and how they were distributed. Did every early galaxy have one, or only a select few? The SKA could potentially find black holes so young and faint that they are virtually invisible to infrared telescopes, peering into an era even closer to the Big Bang than we can currently reach. Together, these upcoming observatories represent a fundamental shift in our quest. We are moving from the age of discovery, finding the brightest beacons, into the age of understanding, mapping the full life cycle. The Nancy Grace Roman Telescope will deliver the broad context, the cosmic census of the adolescent monster population. The square-kilometer array will then reach back even further, trying to capture their faint infant cries. This one-two punch will allow us to piece together the entire story, from mysterious seed to brilliant quasar to silent, dormant giant. We will no longer have to guess about the early universe from a handful of screaming outliers. We will have a rich, detailed family album showing how the first black holes were born, how they grew, and how they ultimately shaped everything that followed. The cosmic dawn is about to come into a sharper, wider, and deeper focus than we ever dreamed possible. The quest to find these ancient seeds leads us directly to the universe's greatest unsolved mystery. The invisible scaffolding of dark matter, which makes up over 85% of the universe's mass, may have played a starring role in the birth of the first black holes. In the dense, hot soup of the primordial cosmos, dark matter was not smoothly spread out. It clumped first, forming vast, invisible gravitational wells called halos. These halos were the cosmic gathering points, the places where ordinary gas, drawn in by that unseen gravity, could collect, cool, and eventually collapse. Without a massive dark matter halo to pull in a deep reservoir of fuel, a young black hole would starve before it could ever become supermassive. The most distant quasars we see, therefore, are not just markers of ancient black holes, they are beacons shining from within the mightiest dark matter structures of the early universe. Their very existence tells us that extraordinarily massive halos formed with shocking speed, but the connection could be even more intimate and strange. Some leading theories propose that dark matter itself might have been the seed. Certain hypothetical dark matter particles, like weakly interacting massive particles, could have gathered so densely in the cores of those early halos that they began to annihilate each other in a burst of energy, destabilizing the region and triggering a direct collapse into a black hole. In another scenario, called primordial black holes, dark matter might not be a sea of invisible particles at all, but a vast population of asteroid mass black holes forged in the Big Bang's first instance. Their collective gravity would explain the dark matter we infer, and a small fraction of them, the lucky few that wandered into gas-rich halos, could have served as the ready-made seeds for the quasars we observe. This means that by mapping the locations, masses, and growth rates of the most distant black holes, we are not just studying the monsters themselves. We are conducting an indirect archaeological dig into the nature of dark matter. Each early quasar is a fossilized imprint of the dark matter halo that birthed and fed it. Their staggering masses tell us how much ordinary matter those halos successfully gathered. Their sheer distance tells us how quickly such immense structures could assemble. If future surveys, like those from the Nancy Grace Roman Telescope, reveal that billion solar mass black holes were common in the universe's first few 100 million years, it would force a radical rewrite of our dark matter models. It would mean dark matter halos grew faster and became more massive earlier than any of our current simulations predict. The light from these distant giants may finally illuminate the dark. That dark matter connection points to a population of black holes we may never see directly. Long before the first brilliant quasars, before even the first stars flickered to life, the universe entered its true dark age. This was a period of profound silence, lasting perhaps 100 million years, where the cosmos was filled only with a cooling fog of neutral hydrogen and helium. No stars, no galaxies, no light. Yet even in that perfect blackness, the seeds of future monsters may have been sown. In the densest knots of that primordial gas, something extraordinary could have happened. Without the complex chemistry of heavier elements to help it cool and fragment, a massive cloud of pure hydrogen might have collapsed in on itself as a single, monolithic entity. It would bypass star formation entirely, crumpling directly into a black hole of perhaps 10,000 solar masses or more. These would be the true dark giants, the universe's first black holes, born not from the death of a star, but from the raw collapse of the cosmos itself. They would be utterly invisible, with no stars to rip apart and no swirling galaxy of gas to feast upon. They would have no glowing accretion disk, no brilliant quasar phase. They would simply sit in the darkness, their immense gravity a silent anchor in the void. For hundreds of millions of years, these dark age black holes might have drifted, growing slowly by sipping on the thin hydrogen fog around them, waiting for the universe to change. Then, as the first galaxies began to coalesce around these pre-existing gravitational pits, they would have been perfectly positioned to become the supermassive hearts we later see blazing as quasars. They are the missing progenitors, the ghostly ancestors to the brilliant beacons we now detect. But if they emit no light, how could we ever hope to find such shadowy beginnings? The answer lies not in light, but in the vibrations of spacetime itself. When two of these primordial giants eventually found each other in the dark, they would spiral together and merge in a cataclysm of gravity. That collision would send powerful ripples through the fabric of the cosmos, gravitational waves that would propagate across the universe for billions of years. Our current observatories, like LIGO and Virgo, are tuned to the higher frequency waves from stellar mass black hole mergers. To hear the deep, low-frequency hum from mergers of supermassive black holes in the cosmic dawn, we need a different kind of ear, one placed in the quiet of space. This is the promise of the Laser Interferometer Space Antenna, or LISA. Planned for the 2030s, LISA will consist of 3 spacecraft flying in a vast triangle millions of kilometers apart, using lasers to measure minute distortions in spacetime. It will be exquisitely sensitive to the low-frequency gravitational waves produced by the mergers of those first dark-age black holes. Listening with LISA would be like tuning into the universe's birth cries, a soundtrack from a time before light could travel freely. A single detection would be a direct signal from the dark ages themselves, confirming that monstrous black holes existed long before the cosmos became transparent. It would open a window into an era forever closed to traditional astronomy, revealing not through photons but through the shudder of gravity itself, how the first structures in the universe truly began. Their silent existence in the dark ages could not last forever. When 2 of these ancient supermassive black holes finally spiraled together, their merger was the most violent event since the Big Bang itself. Picture 2 invisible giants, each weighing billions of suns, locked in a final, fatal dance. As they circle each other at a significant fraction of the speed of light, they churn the fabric of spacetime, sending out powerful ripples known as gravitational waves. These are not gentle waves, they are tsunamis in the structure of reality, propagating across the cosmos for billions of years. The final collision is a flash of pure gravity, a moment where the 2 event horizons touch and become one, releasing more energy in an instant than all the stars in the observable universe combined. But the violence does not end there. Surrounding these black holes are the remnants of their last meals, vast disks of superheated gas and debris. When the black holes merge, these disks are violently shaken, launching jets of material and radiation at near light speed. This catastrophic event is often linked to a short gamma-ray burst, the brightest electromagnetic explosion known in the universe, a flash so brilliant it can outshine an entire galaxy for a few fleeting seconds. Within that unimaginable maelstrom of energy and neutron-rich debris, something miraculous is forged. The intense conditions create a nuclear reactor of cosmic scale, where rapid neutron capture or the R process takes place. This is the alchemy that builds elements heavier than iron. Ordinary stellar fusion cannot create gold, platinum, or uranium. It requires a cataclysm of this magnitude. In the furious outflow from a black hole merger, neutrons are slammed into atomic seeds at an incredible rate, building up the heaviest nuclei in the periodic table. This means the gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers reactors, all were likely born not in the heart of a dying star, but in the violent death throes of colliding black holes or their neutron star counterparts billions of years ago. The atoms that make up our most precious and powerful substances are cosmic souvenirs from the most extreme events in the universe, scattered across space and time until they found their way into the fabric of our world. Gold forged in stellar catastrophes is a cosmic treasure, but the true wealth lies in a complete accounting of the monsters themselves. We have been dazzled by the brilliant record breakers, the quasars that scream across the cosmos. Yet to solve the great mysteries of their birth, we must move beyond the spectacular and conduct a sober census of the invisible. How many supermassive black holes truly existed in the universe's first chapters? Astronomers tackle this by turning to vast sky surveys, painstakingly counting every luminous quasar they can find across immense volumes of space and time. They then use complex statistical models informed by how black holes grow and shine to extrapolate from the few bright beacons to the vast silent majority. The results of this cosmic accounting are startling. While the brilliant billion solar mass quasars from the first billion years are incredibly rare, perhaps only a few hundred in the entire observable universe, the models suggest a hidden ocean of darkness. There were likely millions, perhaps even tens of millions, of lower mass supermassive black holes growing quietly in those early epochs. For every single dazzling quasar we detect, there could have been 10,000 dormant giants of similar mass, or 100,000 smaller ones still feasting modestly, their glow too faint for our current telescopes to see. This hidden population is the missing data in our cosmic ledger. Finding them is not just about completing a list, it is the key to unlocking the seed formation problem. If we only study the rare, ultramassive outliers, we get a skewed picture. It is like trying to understand human growth by only studying professional basketball players. A true census, one that includes all the ordinary, quietly growing black holes, will reveal the typical starting mass. Were most seeds a few hundred solar masses from collapsed stars? Or were they 10,000 solar masses from direct collapse? The relative numbers of small, medium, and giant black holes in the infant universe will point directly to which seeding mechanism was most common. Furthermore, this hidden majority holds the answer to their true impact on galactic evolution. Did every single one of the universe's first galaxies host a central black hole, however small, from the very beginning? Or was it only a privileged few? The difference is profound. If every early galaxy had one, then black holes were a fundamental, universal component in building cosmic structure, a necessary part of a galaxy's DNA. If they were rare, then their influence, while dramatic, was more like a special event, a catastrophe that reshaped only certain neighborhoods. Upcoming observatories, like the Nancy Grace Roman Space Telescope, are designed explicitly for this demographic mission. By finding thousands of faint, early black holes, they will fill in the blank lines of this cosmic census, transforming our view from a gallery of spectacular monsters into a complete population study. Only then will we know the true scale of the shadow that fell across the cosmic dawn. The gold in your jewelry and the iron in your blood are cosmic heirlooms forged in ancient violence and scattered across the eons. But the story of these distant black holes is more than a tale of exotic elements or galactic architecture. It is, in the most literal sense possible, our origin story. Every photon that reaches us from one of these ancient quasars is a messenger that began its journey when the universe was a fraction of its current age. We are not looking at a simulation or a theoretical model. We are directly observing the raw, formative processes that built everything we know. These black holes are our only surviving witnesses to the era when the cosmic dark ages ended, when the first galaxies assembled, and when the fundamental laws of physics were put to their most extreme test. They are not distant curiosities. They are the foundational chapters in the autobiography of the cosmos, written in the language of warped space-time and screaming light. By decoding their light, we are reading the very first pages of that story, pages that describe how a hot, dense, and nearly featureless universe transformed into the rich, structured, and life-bearing cosmos we call home. They offer our deepest, most direct look back in time, a bridge of light and gravity that connects us here and now to the momentous events following the Big Bang itself. In their ancient glow, we see our own beginnings. Our journey to the edge of time reveals a cosmos far more dynamic and violent than we ever imagined. We have chased whispers of light from the universe's first billion years, light stretched and faded by a 13-billion-year voyage across an expanding void. This ancient glow introduced us to impossible giants, supermassive black holes that grew to billions of solar masses in a cosmic heartbeat, defying every comfortable rule about how things grow. Their very existence presents the profound seed problem, a mystery that forces us to consider exotic births from direct gas collapse or even relics of the Big Bang itself. These were not passive inhabitants of the early cosmos. They were its ultimate engines, acting as brilliant, regulating hearts within infant galaxies. Their furious radiation and million-mile-per-hour winds could quench star formation or trigger new bursts of suns, sculpting their galactic homes from the inside out. They were cosmic forgers, creating and scattering the heavy elements that would one day become planets and life. And they were our most stringent laboratories, testing the constancy of physics itself across the vastness of space and time. Each discovery peels back another layer, showing us a universe where the darkest objects built the first light, where destruction and creation are two sides of the same coin. The path forward is illuminated by a new generation of eyes on the sky. The James Webb Space Telescope is already finding these ancient monsters in numbers, revealing their chaotic nurseries. Soon, the Nancy Grace Roman Space Telescope will deliver a cosmic census, while the Gravitational Wave Observatory LISA listens for their collisions in the silent dark ages. Their combined power promises to transform our handful of dazzling outliers into a complete family album of the cosmic dawn. We stand at the threshold of understanding not just how these distant black holes lived, but how they shaped everything that followed, including us. Which single fact from this journey into the deep past reshaped your view of the cosmos the most? Share your mind-blown moment in the comments below. If you crave more journeys to the edge of understanding, subscribe for more cosmic mysteries. Our universe is an ever-expanding story, and we have only just begun to read its first, most spectacular chapters.